Okay, welcome everybody to our last lecture. Let me just mute everybody here. There's some noise. Okay, welcome to our last lecture. Okay, can everybody hear me all right? Great, so today we're wrapping up Introduction to Data Science. We're very excited to share with you your final project. We were super happy to see so many cool projects. And yeah, we'll basically today we'll first look at the best projects, and then we will do like a quick recap and talk a little bit about the class and about future opportunities related to data science and so on. Okay, so let's get started. For the final projects, what we did here, well, first, please remember to fill out this project peer assessment. We send out the link via Slack in the announcements channel, so if you haven't done that already, it is kind of important for us so that teamwork is also fairly rewarded. We want to see like whether there was any kind of like hiccups with the teams. And so now we'll show you the best projects, and we have selected these best projects, and then they selected the best half, the top 4 projects for each of them. And then we reviewed each of these projects individually, and then we looked at the notebooks and we discussed which ones to include in this list of best projects. And so we have 10 projects that we will be showing today. These are all kind of like considered exceptionally good in the class. And there's like also like 3 that we want to especially highlight that we consider like the runner-up and overall winners. And we determine these by kind of like voting. So each of us gets like 3 votes to distribute among the projects. And then the project with the most votes are considered our winners and runner-ups. And so the results of this year's process was that we have 2 winners and 1 runner-up. And those 3 projects get 120% of possible points on the final submission. And then we have 6 honorable mentions, so for a total of 9, which get like 110% of the points. And all of them will be listed in the Hall of Fame on the website. So any questions about the process before I get started with showing those videos? Well, let's take a look at the honorable mentions in no particular order. The first one is COVID-19 as a public health education tool. Let's look at the video.
My name is Brenna. My team is Joyce and Matt, and our team's project is called Public Health Lessons from COVID-19 in Utah. Our objective for this project was to find data-driven insights that could be presented to key decision makers in Utah as lessons learned from the COVID-19 pandemic, with recommendations for pandemic management with future variants, outbreaks, and viruses. The data sources we selected to meet this objective included the COVID-19 dashboard data from the Utah Department of Health, hospital attributes from the American Hospital Directory, and COVID data from the CDC. Our methods included clustering, a time series analysis, odds ratio calculations, hypothesis testing, and decision trees. Our data includes all US states and territories. We started by graphing daily increases of confirmed cases and deaths. We then used k-means to perform clustering based on confirmed cases, deaths, and mortality. Utah had very low mortality, possibly due to the relatively young population. We then analyzed the growth factor based on a 7-day rolling average of COVID-19 infections. Growth factor is a multiplier that grows as an independent variable increases, in our case, the COVID infections. When the growth factor is greater than 1, as is the case with Utah, there may be a spike in cases. Although Utah had low mortality, our growth factor has continued to rise, even higher than New York City as of April 20th. We recommend remaining consistent with safety measures until herd immunity has been obtained. Our key stakeholder is decision makers in Utah during COVID-19, but in examining Utah, we needed to consider the wider region because Utah provides level 1 trauma care to Idaho, Montana, and Wyoming. While Utah is a sort of epicenter for healthcare in the region, we have 40% fewer healthcare resources by population than the US average. This is especially important when we consider that Utah serves this larger community. 1 in every 25 cases in Utah was hospitalized, and for every 10 hospitalizations, there was 1 ICU admission. In the graph, you can see the COVID proportion of ICU utilization. Utah ICUs reached functional capacity on 57 days. Decreasing cases by just 5% would have decreased this number by 18 days. It's important to avoid hospital admissions because COVID hospitalizations impact the healthcare system as a whole. We created a model to predict risk of hospitalization based on patient attributes, and our decision tree predicted hospitalization with 85% accuracy. We learned that age, gender, and pre-existing conditions were the strongest predictors. With that in mind, we calculated odds ratios for reported conditions. Kidney disease had the highest odds of hospitalization, and we were surprised to learn that those with lowest odds were respiratory in nature. This demonstrates that there's an underlying etiology that is significantly contributing to the severity of the disease. Overall, we recommend better collaboration between states, caution with the chronically ill, monitoring seemingly unrelated conditions, and focusing on gathering better data.
Okay, this was a great project. This was by Brenna Kelly, Rejoice Fawn, and Matthew Hoffman. So congratulations. The second project we want to look at, let's see. Second project in this honorable mention category is Social Determinants of Health to be Determined by Brian Clark, Courtney Rogers, Adrian Reyes Miranda. So let's look at the video.
Observed pattern in the health status literature. While older adults with epilepsy are more resilient in facing chronic illness, and middle-aged adults fare the worst, this measured by self-reported health status. We wanted to study this pattern and investigate the role social determinants of health play in this. To do so, we use the data from the HINTS survey, which is conducted by the National Cancer Institute and collects data on how Americans consume information related to cancer. The data includes over 350 variables and 3,500 respondents. Question number 1. Do the people with cancer in our data set follow the pattern of adapting to health over time? To answer this question, we use exploratory data analysis, mode for oversampling, chi-square test, and logistic regression. Among the people with cancer in our data set, most report good health, but it's good to know that the middle-aged group reports the highest percentage of poor health among the groups at 27%. However, there seems to be no relationship between age group and good health status in univariate analysis. After running a logistic regression model on balanced data and controlling for variables like BMI and physical and psychological comorbidities, age becomes a significant predictor of good health. This result suggests that the odds of having good health is 5% lower as age increases by a unit of 1. Health status seems to worsen as age increases, but not by too much. Some of the significant predictors for the good health variable in our cancer subset. All p-values below 0.05.
How do social determinants of health like disability, race, language, education, and gender influence reported health status? Question, chi-square tests and a random forest classifier were used. Chi-square test, 9 out of the 15 features had a significant relationship with the reported health status. Graduating from high school, being proficient at English, being white, having health insurance, and being born in the USA all had a positive correlation with health status, whereas being disabled, aging, having completed the survey in Spanish, and being Black all had a negative correlation. The random forest classifier had an 82.46% accuracy on the test data, but it did not perform well when predicting for participants with poor health. Though the features alone did not create a good model for predicting health, the chi-square test provided evidence that social factors do have an impact on health.
Question 3. How do socioeconomic disparities in access to resources affect self-reported health status? Methodology. Spearman's rank correlation, ordered logistic regression, supervised multi-class classification. When looking down our review column, general health, we see that there's a weak, albeit positive correlation with education, income range, and how often people exercise. Moving on, we've chosen to measure the statistical significance between our target variable, general health, and the other variables using ordered logistic regression. After passing our statistically significant variables onto our multi-class predictive models, namely Random Forest, KNN, SVM, and AdaBoost, we observed that each model is suffering from a bit of bias or underfitting. In conclusion, looking at both that out of the socioeconomic factors represented by the variables included are found to be statistically significant predictors and possibly contributors to one's overall perceived health status.
Okay, also a great project. Our next honorable mention is Improving Healthcare Documentation Using NLP by Max Sanders and Andreas Martinson. Congratulations.
Hello, everyone. My name is Andreas Martinson, and this is my final project. What I decided to do was to build a natural language processing web app, and it's intended to be used in hospitals or clinics, and it's for physicians to put in their clinical notes and then get back some results, some billing codes from the encounter that they had with the patient. I built this using Streamlit for the front end, and then on the back end, there's a lot of machine learning model training. There's 6 machine learning models that were used to create this, and I'll explain in a second why there are 6. So basically, this data comes from Mimic, and Mimic is a database that has over 40,000 patients tracked over 11 years, and there's over 2 million rows of clinical notes, and it's frequently used for natural language processing. So in this example, I have it already pulled up since I don't have a ton of time, but with the generated text option selected, there's the notes that were auto-filled here. If the text input was selected, this would clear, and the physician could put in the notes here. The prediction that was made in this instance was an aortic valve disorder. If you just do a quick search for aortic, you can see that it is in the text, and that seems be probable that that is the primary diagnosis. The model predicted it with 98% confidence that this is the case. And then HCC is just a term of hierarchical condition categories. That's a value-based care term. You can look it up if you're interested. So as far as the procedures that were performed for the patient during that encounter, I broke that down into 5 different categories, and there's a prediction for each one. So there's 1 prediction for the primary diagnosis, and then 5 predictions, 1 for each CPT category. Hover over, you can see a description for each one. Those descriptions and the crosswalk to the SNOMED CT codes are from the UMLS Metathesaurus API that is connected to as well. You can see that all these change for each one, and this is just built using Altair. If the physicians are curious what resulted in these predictions, you can see the top 10 features for the ICD-9 codes. So you can see valve replacement, aortic stenosis, and aortic were very predictive. And then if you're interested why this CPT code category was predicted, you could also go down to surgery and see those explanations as well. That's a general overview of the project. And thanks for listening. Bye.
Okay, another great project. So the next runner-up here is, or the next honorable mention is, Did COVID Reduce Other Illness Counts by Paul Carden, Chantal Lepin, and Cameron Pascua. Okay, let's take a look at the video.
Our group studied how COVID-19 affects other common medical conditions.
In our analysis, we investigated the potential effects of COVID-19 on various other medical conditions, including other respiratory diseases such as pneumonia and influenza, pregnancy and birth, and mental health such as anxiety and depression. Our main methods of analysis were linear regression and hypothesis testing.
Here we have death counts of COVID-19, pneumonia, and influenza per week. And we see that on the left, COVID-19 and pneumonia seem to spike together, while influenza death counts on the right actually drop with the first COVID-19 and pneumonia spikes. We then wanted to look at the correlation between the data, and we can see that the correlation between COVID-19 and pneumonia is 0.98, which is extremely high. The scatter matrix also shows a high correlation between the two groups. So finally, we decided to perform a linear regression to model the COVID-19 data, and we found that using both pneumonia and influenza death counts, we were able to produce the best model and the highest R-squared values of.
Next, using hypothesis testing, we were able to determine that the number of births declined from raged on. The adequacy of prenatal care also declined significantly after the COVID restrictions started in March. Consider that the hospitals were strained for time and resources. And the main takeaway here is that the infant characteristics were worse in every category across every demographic for women who contracted COVID-19 while pregnant. The NICU is only used when babies are born early, have health problems, or a difficult birth, and is a great indicator of poor infant health.
Based on responses from a survey done by the CDC and the Census Bureau, depression and anxiety symptoms were estimated. In 2019, 11% of adults in the US showed symptoms of mental health versus an average of 38% in the past year during COVID. To specifically look at anxiety rates in COVID-19 cases, we see the first COVID peak around July 2020 corresponds with the peak in anxiety symptoms of adults. Similarly, the second COVID peak in December 2020 corresponds with another peak in anxiety cases. Moving on to depression symptoms data, we see a similar trend in adults reporting symptoms of depression in higher percentages with COVID peaks. From this project, we learned that COVID-19 and pneumonia data are highly correlated. Pregnancy and birth rates significantly declined, and symptoms of depression and anxiety have risen and followed similar trends with COVID cases. Thank you.
Okay. Now, the next honorable mention here is COVID-19 vaccine sentiment analysis and rate prediction by Ike Grisalas, Mary Munch, and Jameson McCarthy.
The present-day COVID-19 pandemic has brought a lot of issues to light, but one of the most impactful facing our society today is the social acceptance of vaccinations. In this project, we explored sentiments related to the COVID-19 vaccines paired with demographic data of certain counties in Utah in order to understand general trends of attitudes for certain demographics and how that affects vaccine coverage. Vaccination data was acquired by directly contacting the Utah Department of Health, the demographic data from the U.S. Census website, and the sentiment analysis from a Facebook survey on vaccination opinions gathered daily from thousands of Utah users gathered by the Delphi group out of Carnegie Mellon University. We then loaded the relevant data into a master CSV file and used Opinion as data frame to explore, analyze, and make predictions. This was done by finding correlations between demographic data and vaccine coverage and creating multilinear regression models using different parameters.
We decided to focus on 7 counties, incorporating the following parameters as we can see on the left here. In the middle graph, the median age rests around 30 years, with the exception of Summit County with 40 years. On the right graph, we see the majority of the population being white, with the exception of San Juan having a high proportion of American Indian and Alaska Native individuals. However, since we are creating models to predict the coverage within Utah only, this is relatively a diverse set of data. We are predicting the vaccine coverage denoted by first dose. This data spans 3 months starting on January 1st. We can see that San Juan and Summit County had a more aggressive coverage rate, especially at the 1 and 2 month mark respectively, whereas the other 5 counties follow a similar trend. Our goal is to then accurately predict these plots using gathered geographic and sentiment data, and then assess the model's ability to predict on a wider geographic area. Our main approach was to use multilinear regression models that were created by splitting our data into training and testing data sets, in which we use cross-validation to acquire the best parameters, as we can see on the right. For the counties where sentiment data was available, namely Davis, Salt Lake, and Utah County, including sentiment data changes our accuracy only by a slight margin, decreasing by 0.2% for Davis County and increasing by 0.2% for Salt Lake County. Utah County remained the same. Lastly, we test our model's ability to accurately predict the vaccine coverage in all of Utah using the data from our 7 counties. We can see that without sentiment data, that our model is quite impressive on its own, with an accuracy of roughly 98.6%. Including the sentiment data gives a very slight increase, with almost a 99% accuracy. As we can see, the regression model that we have created shows promise in use on a wider geographic area.
We felt that the best portion of our project is the highly predictive nature of our models using the demographic and sentiment data. This is relevant to effectively vaccinate while also minimizing vaccine waste, as well as predict how long until a country reaches herd immunity. The most insightful component of this project was the difficulty in locating reliable data. This was the most time-consuming as well as required the most trial and error, specifically for the sentiment data, which at times we consider dropping entirely. The most important factor we would like our audience to take away is that there are more factors that contribute to the distribution of vaccines outside of availability, infrastructure, and access. These elements are necessary but meaningless if the residents of the area carry attitudes that impede the distribution and deployment of vaccines. These attitudes are unpredictable, so developing this model to understand sentiment concurrently with demographic data allows us to effectively create predictive models of vaccine coverage.
Okay, another great project. And now the next honorable mention is NBA MVP. Does the voting match the statistics? By Courtney Yoshimoto and Mark Ruiz.
Hello, my name is Courtney Yoshimoto and my partner's name is
Mark Ruiz.
We're going to be presenting our project titled NBA MVP, Do the Stats Match the Results? Our project consists of 3 essential components: data collection, data cleaning, and data analysis. Before we get into data collection, we want to give you a brief overview on how the voting process works for choosing the NBA MVP. The NBA has been awarding the MVP since 1955, but since 2010 there have been 101 ballots, 100 by sports writers and broadcasters and 1 by online fans. The voting ballot consists of ranking players from 1 to 5, and the first place player gets the most points, with the 5th place player getting the least, and at the end all the ballot points.
For our data acquisition process, we scrape stats from all players given at least 1 vote for MVP from 2010 up to 2019 from basketballreference.com. After scraping all the data, we then stored data for each year into CSV files, and then we were able to combine all CSV files into one data frame. Once we had all the data into a single data frame, we then were able to store just the MVPs with the rank 1 into a separate data frame in order to help with our analysis. As for our data cleansing, we stored our data into data frames and then cleansed either ints or floats.
After that, we went to our data analysis, and we started by using our target value as our share, which is analyzing our data was to choose the stat we thought would be most correlated to the MVP winner, which we chose to look at average points per game. Unfortunately, when running a linear regression model on this, the R-squared number was extremely small, and visibly from our graph we can see there was little to no correlation there. We then decided to visualize our correlation matrix so we can see all the stats correlation to the share value. After that, we used SVR in order to run test accuracy of different train and test models. First, we used all the stats, and the model gave us an accuracy of about 24%. So then we used rainforest regression to show the most important stats to share value. From these results, we dropped the lowest 3 stats, which were blocks, total rebounds, and 3-point percentage. With the new model, accuracy improvements went to 54%. After this, we used KNN neighbors with ranges of K from 1 to 15, and from that model we got an accuracy of 90% and 91% for test with K equals 3, which was a huge improvement. Overall, this project was very interesting, and from our results we can see that the MVP is not just chosen off individual stats.
Okay. Great project as well. So that leaves us with the one runner-up, which is mRNA expression in stem cell differentiation of zebrafish testes by Nora Pearson, Darren Lewell, and Matt Poulsen. Congratulations.
All right, it's rolling.
So we are Darren, Matt, and Noah, and we are exploring mRNA expression and stem cell differentiation. So we are working with single cell RNA sequencing data sets, which gives us an mRNA inventory for each cell. And the testis in particular has cells differentiating at multiple points. So our objective is to explore the differentially expressed genes for these different cell states as they're differentiating, and then characterize what those genes are involved in, which Matt will go into a little more detail on.
In order to find out what the function of those genes are, we used gene ontologies, which we got from UniProt website, and mapped those to the different genes in the cells to be able to tell which cells are responsible for which functions.
All right, and so with our genetic data and our gene ontologies, which are the functions of those genes, we started working on our toy data set to optimize to flesh out the bugs in our process. We started by applying a two-dimensional UMAP reduction on our data. We moved forward and applied some clustering on our data and visualized that with our reduced data. And then we created a tool where we can select a region of interest. And well, my computer's frozen right now, but these ontologies down here on the bottom change in response to the selected region of interest. So this allows us to view how function changes as a function of the UMAP reduction.
So the main data that we worked with was a data set from the Gagnon lab, straight from a zebrafish dissected testis. And it was quite a large data set, so we needed to subset by the cell quality and subset by the most variable genes to cut that down quite a bit. So we ran UMAP and clustering, and then made this tool. So for each cluster, you can specify which cluster you're looking at, and then it will show you the highest expressed genes, their descriptions, and then it generates a heat map of each cell in that cluster so that you can visualize the whole cluster. And then you go down to the bottom, and then we will look at the version for this main data set, which is a lot larger, and will show you the ontologies as you go through the clusters, which allows us to characterize these clusters and the cell states they represent.
All right, thanks for watching.
Okay, we really like this project because it just was a great application of many of the tools that we talked about in class and brought everything really nicely together. And then we have the two winners, and the winners are now listed in no particular order. The first winner is Analysis of Biking GPS Data by Zane Kincaid, Bobby Covington, and Peter Morgan. Congratulations.
For our project, we did a comparison of my mountain biking data with one of my friend's mountain biking datas that we both recorded using GPS of all our rides, as well as looking at our ozone exposure during our rides. We made these line plots showing rolling averages of the distance, elevation gain, and duration of both of our rides. We also made calendar plots that show the duration and elevation of our gain and elevation gain of our rides by day of the week and time of the year, so you can see what days of the week we're most likely to ride and seasonally when we're most likely to ride. Bobby?
For the ozone concentrations, we also used line plots just to see the ozone concentration over time. And then there are a little bit of missing data because these are actual sensors being used, and sometimes sensors do break. So we can see this over a few years. And then to compare what the ozone concentrations were with the bike rides, we made histograms. So you can see that the average concentration of the ozone on a given ride and like how often that occurred. We are just looking at the values, and we want to make sure that those rides consistently stay under 16 parts per million of ozone concentration. We have that for Zane and Tor.
So our exploratory analysis revealed that there are some fundamentally different patterns between Zane's and Tor's riding habits. And so for the first part of our additional analysis, we decided to build a decision tree classification model to see if there were actually significant differences. And turns out there were. We got an accuracy of about 88%, which is really good. We also wanted to develop better ways to predict ozone levels. And so we first made these seaborne plots, and the main thing that they showed us is that higher winds tend to stabilize ozone concentrations. Additionally, we did spectral density analysis, and the main insight we gained from that was that there tends to be a once daily peak in ozone concentrations around 12 o'clock noon each day. And so that can help a rider plan when to ride to avoid high ozone levels. And then lastly, and probably the most interesting aspect of our analysis are these brushable graphs we made for each rider, where you can see each ride is in this plot. And as we go to each one, we can see the ozone level of that day, but we can also see the elevation gain, the lapse time, and so forth corresponding to those rides. So this can give some extra insights into how a rider can better plan their rides to avoid high ozone. So we achieved our main goals for this project. We were able to tell how to avoid high ozone levels as a bike rider, but we were also able to gain insights that could be used to do further study, including studying the health impacts of ozone levels on different riders.
Okay, congratulations, very nice project. And then our final winner is Seasonal Dust Trends in Northern Utah by Christopher Rapp, Parth Rastogi, and
Our project is Seasonal Dust Trends in Northern Utah. Our work is motivated on current and past research attributing wind events across the Great Salt Lake to elevated dust concentrations in the Salt Lake Valley. Our project is designed around applying a primitive approach of correlating wind data to particulate matter. If we do show such a relationship, then it strengthens a theory wherein researchers in Utah that a drying lake bed increases the prevalence of dust along the Wasatch Front. Our data acquisition was fairly straightforward, however the data wrangling was very involved. We used a method of reading individual files and appending them to the end of a data frame. Our data included hourly PM 2.5, EPA daily PM data, and meteorological variables for 20 sites, 5 of which were in the Salt Lake Valley. The other 15 positions are Great Salt Lake. For all data sets, we included the past 20 years of data. Moving forward to the seasonal analysis section, we remind ourselves that the main research question we had was to identify seasonal relationships between wind and particulate matter, which we could infer was dust. We designed a function to compute daily averages per site for all wind directions and for a subset of wind directions, specifically between west and north. As we are investigating the wind trends across the Great Salt Lake, this wind direction is necessary in comparing to observations in the Salt Lake Valley. We then must pair our data with the pollution values in Salt Lake so we can investigate potential relationships. We used Seaborn's paired plot functionality to look at our paired data by season and computed Spearman correlation coefficients for each relationship. As we are investigating how wind speeds across the Great Salt Lake affect PM, we filter wind speeds across the Great Salt Lake sites specifically. The first is all wind speeds, and we can notice the wintertime inversion trend where there's a strong relationship between PM 2.5 and PM 10 during the winter. This trend disappears, however, once we observe only wind speeds higher than 5. When we select wind speeds above 10, we see that the spring is the predominant season for high wind speed events. We then apply both the Wilcoxon-Rank sums test and student tease test to test for significance. We use both to check results using a parametric and non-parametric approach. A result we are interested in is the relationship between Salt Lake and PM10, which is shown to be statistically significant, despite the plots above, which did not show a strong linear trend. This conclusion section discusses this in detail, where we may be looking at a nonlinear relationship, and we are trying to use a linear plot to try to describe that, which will not work. Finally, we generated wind roses to visualize our data for each site. In all, we did find a relationship between high wind speeds across the Great Salt Lake and PM10 in the Salt Lake Valley. However, our primitive approach is not the most convincing, and further methods, as discussed in the introduction, would be necessary to confirm our results. Such would be cross-referencing wildfire data, looking at aerosol optical depth, and angstrom exponent, which are all satellite measurements This would help us confirm whether we are looking at dust or not. PM10 is likely the dust measurement, but we cannot be certain.
Okay, great. That concludes our projects. So overall, I have to say we were very excited to see so many cool projects. And even if you didn't make this list, there's multiple projects that we thought are really also excellent, but we had to pick some in the interest of time here. So with that, I'll hand it over to Anna, who will be giving a brief recap of everything that was happening in this year.
Okay, thanks, Alex. Get my screen set up. Okay, yeah, so just as Alex said, we got a lot of great projects. It was a lot of fun seeing what you guys worked on, and yeah, great job. And I'm just going to do here a little recap, looking back on what we learned over the course of this semester, and then also what we didn't have time to talk about. I'll just talk a little briefly about a few of those topics in case you want to learn more about them. So what did we learn? Well, lots of programming, lots of Python. So if you had never programmed in Python before, this was probably, you know, a pretty steep learning curve. I mean, you just sort of got thrown in, but we learned a lot about for loops, about functions, how to program in Jupyter notebooks, and using many different Python libraries, various tasks. We also learned about all the different data structures in Python, lists, dictionaries, series, pandas, data frames, etc. And also the ever important data cleaning stage. So we got some practice cleaning and aggregating and reshaping data in Python. And then we learned a little bit about version control, including Git and GitHub, by sharing our resources in the GitHub repository. So hopefully that has also been a really useful skill that you'll take with you after the class. Okay, we learned a lot about data collection. We got our hands dirty a little bit with web scraping, with inspecting and parsing HTML, and learning how to retrieve websites. And we also looked at various APIs and talked a little bit about working with databases. We talked about multiple different visualization methods and all of the, not all of them, but a number of the Python packages that have useful tools for data visualization, including Matplotlib, Seaborn, Altair, and GraphX. And we learned some of the basic plots that we can make with these packages, like histograms, scatter plot matrices, decision trees, etc. And you guys used a lot of these in your projects, which was great. Okay, and then we talked some statistics. So we just did sort of the basics that we needed to get started on hypothesis testing and statistical inference. We talked about various distributions, including Bernoulli, binomial, and normal distributions, and sort of the basics of doing hypothesis testing, and also sort of this special case of A/B testing. And we learned about how widespread that is for, you know, large companies testing their products, or in their layouts, I should say. Okay, we also looked at time series. We, didn't spend a lot of time on time series, so there's a lot more that you could go into there, but we sort of looked at some examples of stock data, getting and visualizing stock data, how to compute moving averages, the bigger the average, the smoother you get, and how you can create some basic trading strategies, even from these basic tools. Okay, and then we also spent, a bit of time focusing on a really important topic in data science, which is prediction. So specifically, we looked at regression and started off in the simplest case of a linear regression where you have single predictor variable and you're trying to predict a response variable. And then we generalized multilinear regression where you have a lot of predictors, and also nonlinear models where you have interaction terms or quadratic terms. And we talked about, as wonderful as linear regression is, it's still sometimes difficult to draw strong conclusions because of all the confounding variables that you may encounter in an actual data set. And we also talked about regression in the inferential context, where you're also doing statistical inference on the underlying parameters involved, so how to interpret those results and run them in Python. And we saw some great ways to do these things in both stats models and scikit-learn. Okay, we also talked about classification. So shifting to the, I guess here we're still talking about supervised learning for classification now, not clustering. And we learned a number of different methods for this, k-nearest neighbors, decision trees, support vector machines, and neural networks, which are more and more popular these days. And we looked at some kind of general topics, including generalizability and cross-validation, which are important for all of these methods, and also looked at implementing them in scikit-learn and using TensorFlow for neural networks. Okay, and we also looked at clustering. So we looked at how to do unsupervised learning where you don't have labels, but you're just trying to group similar data points together. And we talked about various methods for this, including k-means, probably the most well-known method, but also various hierarchical clustering methods which organize your data into a tree structure where sort of points are agglomeratively merged into clusters in a dendrogram plot. And we also discussed dbSCAN, a very popular density-based method for doing clustering, and saw how to run all of these algorithms in scikit-learn. And we did dimensionality reduction, which is very important for data science. It's important both for visualizing the data in low dimensions and also for getting better results for very noisy high dimensional data. And so we looked specifically at principal component analysis, which is the most basic way of doing dimension reduction. I encourage you to look at other methods if you're interested in this topic. There are lots of different things out there. Okay, and we also talked about natural language processing. We were very fortunate to have Dr. Vivek Srikumar share with us his insights in natural language processing. This is actually not a topic that I know a whole lot about personally, but we learned about semantic analysis and expressions, and also using the natural language toolkit. Okay, and then we were also fortunate to have Devin talk to us about networks, and learned a lot about networks, including how to define various centrality measures, to characterize networks, the very famous PageRank algorithm, and pathfinding algorithms, and also ways of visualizing graphs. Okay, and then we also, spent a couple lectures on neural networks and sort of diving into this area of deep learning that can be useful both for classification and regression problems. And so what we saw here is really impressive performance with these methods on a lot of real world data. But this sort of comes at a price, and the price being that you usually need a lot of data to train these models, and they can be difficult to train. So there's a lot of skill that goes into how to properly design and train a neural network. And because the models are so complex, they're notoriously difficult to interpret. And we looked at doing this with TensorFlow and specifically with Keras. Okay, and we also talked a little bit about ethics in data analysis using some of Dr. Jagadish's course materials from the University of Michigan. So we looked at what are ethics? What is informed consent? This sort of tricky question of who owns the data when the data is about you, but somebody else collected it. Are algorithms fair? What are some of the things that we don't necessarily think about, but that really have can potentially have a strong impact on society? So what are the consequences to society of what we do as data scientists? Okay, so that was sort of a whirlwind of all the stuff that we've talked about this semester. It's a lot, so you should be proud of yourselves for making it through so much substantial material. But even with as much as we covered, there's still many topics that we didn't have time to touch on, and I'll just mention a couple briefly right now. So what is missing from the course, or what would we have liked to talk about if we had had more time? So one really interesting topic is reinforcement learning. Reinforcement learning is basically the third pillar of learning. So we have unsupervised learning, we talked about that, supervised learning, we talked about that a lot, and then reinforcement learning. In reinforcement learning, you have an agent who is taking actions and is trying to maximize a reward. So the agent is trying to develop the best strategy, the best actions to take to maximize reward. This area has close connections with optimal control, and it's interesting. It's different than the models that we have discussed in that it can evolve over time. So the agent can develop a better strategy as they get more experience. And another really interesting topic is recommender systems. So for recommender systems, you may have a group of users that are, say, the rows in a really big matrix, and then you may have items corresponding to columns. So for example, think about Netflix, where you have all of your Netflix users, and then the items are all of the different movies on Netflix. And then you have ratings for some of them, but you have a lot of missing data there. Some subset of the users, rate some subset of the movies. And then what Netflix wants to do is come up with an algorithm that can use that sort of limited amount of data that it has to make predictions and to predict for a user what other movies they're going to like that they haven't seen based on the movies that they have rated. They get some sort of idea about what they like, and then they can make good predictions about other similar things that they'll like. And so from a mathematical perspective, this problem is known as matrix completion, right? Where we can think about, let's say we observe the blue numbers or the blue entries in the matrix, the white ones are sort of missing. And we have this really, really, really large matrix, but the idea is that there is a low dimensional structure there that allows us to make those predictions and fill in those numbers with some accuracy. And in 2009, Netflix actually offered a $1 million prize to the winner of competition for whoever could make the best algorithm for doing this. So there is money to be made in these methods. Okay, and then with ensemble methods, well, this is sort of, I guess, a meta term that encompasses encompasses a number of different methods, but the idea here is that we make use of multiple different learning algorithms. So we use multiple learning algorithms on the same problem to get better performance. So one example of this is bootstrapping and bagging. So in bootstrapping, what you do is you take a random sample with replacement from your data, and in bagging, what you do is, you take a bunch of those random samples with replacement. On each of those random samples with replacement, you train a model, and then you aggregate the results of all of those different models together. So for example, if you're doing regression, you would then average the output of all of those models. Or if you're doing classification, you can have each model have a vote and you go with the most popular vote. And this is known as bagging, which is short for bootstrapping aggregation, or aggregating bootstrapping. Okay, and when this idea is used for decision trees, you get what's known as a random forest model. Okay, and then another sort of big area of statistical theory that we didn't have time to talk about are Bayesian methods. So the philosophy here is that you start off with some data set. So say you start off with data set X, and you assume that there's some kind of probabilistic model that generates this data, but that this model is governed by certain parameters, theta, that are unknown, right? So maybe you assume that you have a mixture of Gaussians, but you don't know the means and covariance matrices of those Gaussians. So you have some assumptions on the model that generated the data, but the underlying parameters for these models are unknown. So we'll call those theta. What you do assume is you assume some prior distribution on those parameters. So you assume knowledge of P of theta, probability of theta, and this is known as the prior distribution. So sort of then you look also at the sampling distribution, or the likelihood function. So this is defined as the distribution of the observed data conditional on its parameters. So P of X, the data, given theta, the parameters of the model. So this quantity, actually, P of X given theta, this can be explicitly computed. So that's the advantage. In general, you're more interested in P of theta given X, but what can you actually compute? You can actually compute P of X given theta. But since you can compute this, you can then construct what's known as the marginal likelihood. And this is the distribution of the observed data over the parameters. So then P of X can be computed by integrating over all the parameters of this likelihood function, P of X given theta times P of theta. And then, so when you're talking about sort of the Bayesian philosophy, the posterior distribution is really important. So the posterior distribution is the distribution of the parameters after taking into account the observed data. And this can be computed with Bayes' rule. So what you're really interested in maximizing in this Bayesian philosophy is this posterior distribution, P of theta given X. By Bayes' rule, it can be computed like this, and it's just proportional to the likelihood function, P of X given theta, times the prior distribution, P of theta. Right, so which this is known or assumed, and then this is computable under the model, so you can then maximize that. And whatever maximizes that would then be referred to as a Bayesian estimator for the data. Okay. So another important topic is research reproducibility. And this is a very important topic. What do you mean research reproducibility? Well, there's a lot of papers that are published and studies that are done reporting really interesting results, but that people have then had a hard time afterwards reproducing those results or verifying that they're actually true. And researchers do have a bit of bias because, you know, they want to find interesting results, they want to get published. So this can lead to some pressure to find interesting results in your data, whether they're there or not. So it's become increasingly important to have standards for reproducibility. And these generally take the form of, you know, making your data public and then making your code and your scripts public, so that along with the publication, you may also post, you know, all of the data and all of the code that you ran on the data in order to generate your results, so that someone can go through and explicitly see all of your settings, all of the assumptions that you did, and also, you know, try their own methods on the data to see what happens. Okay, so I think that's all I was going to say. I'll hand it back to Alex to talk about where can you learn more. But I just want to say it's been a pleasure having you all in class, and best of luck to you, and have a great summer.
Okay, thanks, Anna. So yeah, I just wanted to give you a couple of pointers. If you found this class intriguing, if you really want to learn more, dive deeper into some of the topics that we covered, here are some pointers for you. So the first kind of like resource for everything data science related is this new Utah Center for Data Science. Both Anna and I are members of the center. And this website, datascience.utah.edu, collects all kinds of information related to data science across campus. It lists like academic programs that are related to data science. There is like a seminar series that has been kind of like suspended for COVID, but is now starting back up, that is public. So if you want to hear data science speakers, this is the place to go. And there's also, well, I'll talk about this a little bit later. There's some other courses of interest, either in math or in computer science. I'm not going to read them here in detail, but I'll make those slides available later. So if you want to learn more about any of those topics, please take a look at these courses here. There's also like degree programs, such as the MStat degree, which is the Master of Statistics program, which has a data science option. You can look at that program at mstat.utah.edu. Of course, we have a master's program in computer science. We have, but there's like one specific to like data management and analysis. This is designed for full-time students. The MStat, I think, is like also, like say, more accommodating to people who work at the same time. This here is like typically assumes that you're a full-time student, and it has like various core classes related to machine learning, data mining, data management, and so on. From the CS department, there's also the Big Data certificate, which is designed for professionals working full-time. It does go through many of the higher level CS data courses. It requires an undergraduate degree, but it's not an MS degree. It's just like a certificate. So you get the certificate, and if you want to, after a certificate, you can switch into a full-on master's program. And then I also briefly wanted to advertise the Data Science Day. This is like an annual event. It didn't happen last fall because of COVID, but this fall it will be happening again. So the Data Science Day is like welcoming all students, staff, and faculty to present a poster or a demo. And so what you could do if you really liked your project in this class is you could sign up your project to be presented at the Data Science Day as a poster. And there's also a speaker lineup. There's usually like one big name keynote speaker and then multiple additional speakers that talk about various topics. And it's also often combined with like the Career Expo, where like various companies that hire in data science will visit, and you can meet potential employers. Now, I want to talk a little bit about feedback, how you can give us feedback. So first, I would really encourage you all to do the course evaluation. Take 5 minutes to evaluate this course. the evaluations are important for us to improve the course and our teaching, and to really make this like worthwhile for you. We will give everybody 0.5% bonus on your grade if more than 70% of the class evaluate this course. So it's kind of like a tragedy of the common thing. So you have to go in and you have to evaluate, and you have to hope that your peers are also going to evaluate. And if we have more than 70% by the grading deadline, then everybody gets a 0.5% bonus. So I hope you, that will encourages you, but I hope that you anyways are interested in doing this. And now for the next part, I wanted to like just ask informally here to get some feedback from everybody. But to do that, I will stop sharing my screen, but I will also stop the YouTube recording, because I think this is something that we want to